Our final presenter is Aleyna La Croix, a PhD student at Dartmouth College, and they'll be presenting on shocking revelations in cryogelation, sparking musculoskeletal regeneration. Take it away.
Thanks for having me. Electricity powers our homes, our cars, our world, but it also powers something a little bit more personal. It powers our bodies. During development and healing, electrical signals guide the regeneration of bone and muscle. Muscle responds directly to electrical cues by contracting and growing in response. Meanwhile, bone is naturally piezoelectric. It generates electrical fields when stressed, which stimulates repair and remodeling. But in high-impact injuries, such as battlefield trauma or severe fractures, both bone and muscle are destroyed. That means we lose not just structural support, but also the native electrical signaling that drives regeneration. My project aims to restore both structure and signaling. Our approach is to create a conductive tissue-engineered musculoskeletal scaffold. For bone, we use a macroporous cryogel to mimic its stiff, porous environment. For muscle, we utilize a more elastic and compliant hydrogel. On their own, these scaffolds are able to act as a support structure. However, they're unable to restore the lost electrical signals. To restore the electric potential, we first improve the conductivity of our scaffolds by incorporating MAXine, which is a 2D nanomaterial which has been shown to be highly conductive and biocompatible. So looking at the middle graph, we can see how the addition of MAXine has increased the conductivity of our scaffolds. We compared cyclic voltammetry measurements between our scaffolds with the addition of 70% MAXine ink, which is shown in red, with the control chitosan gelatin, which is shown in blue. In both hydrogel results, which are on top, and cryogel results on the bottom, we see clear higher peaks in the MAXine results in red, showing a more efficient electron transfer, which is indicative of higher conductivity. So having created our conductive scaffolds, our next step is to bring these scaffolds to life. So we seed our scaffolds with bone marrow-derived mesenchymal stem cells. And utilizing an electrical stimulation chamber, we're able to apply controlled electrical stimulation to guide cell differentiation in a way that replicates native bioelectric cues. The improved conductivity allows us to deliver these electric fields evenly throughout our scaffold. With varying control parameters, we're working to induce both osteogenic and myogenic differentiation in the respective scaffolds. And by combining bone and muscle scaffolds into a single electrically active construct, our goal is to restore the native bioelectric cues and reciprocal signaling that drives true musculoskeletal healing. Our final step would be to implant these in vivo to restore musculoskeletal function. And our ultimate goal is to create an electrically active construct that can regrow what was lost in injury and trauma. Thank you.
Thank you, Aleyna. Is there any questions? I have a question. Sorry.
No, go ahead.
Regarding your in vivo model, what kind of in vivo animal model you're exactly looking at?
I think we're going to begin with mouse.
Okay. And then your bone fracture is going to be an osteotomy critical size?
Yes, with both bone and muscle simultaneously.
Okay, thank you. Is there any other questions? I have a question in chat from Lord Mara. It says, best ways or methods for electric stimulation. I'm not sure if that's a question or...
I can answer. It depends on in vivo or in vitro. Right now, in vivo, there are bone stimulators on the market that can apply electric field via either like DC, AC, or pulse electromagnetic fields, as well as there's some implantable kind of devices that are utilized as well.
Thank you. Do we have any other questions?
I would have a quick one. Quick question. How do you control the differentiation of these cells just by different electric stimuli or additional growth factors?
Right now, just the electrical stimulation. So with the different parameters. Bone, typically, it's pretty well studied that it's about 1.2 volts at a lower kind of frequency, around 100 hertz. And I think we're still trying to find the appropriate stimulation parameters for muscle, but it's a lot lower at around like 300 millivolts. And with a lower frequency, about 10 hertz is roughly that range we're looking at.
Great.
Thank you very much. This is the time, and I believe this is the last presentation.